For this homework, we're going to also be looking at confidence intervals, but instead of confidence intervals for a proportion, a population proportion like we did in the last homework, we're going to be using a population mean. So again, as a little bit of a repeat, the general form for any confidence interval is going to be your point estimate plus or minus your margin of error. Now this is the same that is true for this one as well, for the population mean. So our point estimate is going to be x bar plus or minus our margin of error. But our margin of error is going to be made up of z alpha over 2 sigma over the square root of n, or it could be made up of x bar plus or minus t, and we're not familiar with the t yet, but we will be, alpha over 2, and this is part of the subscript n minus 1 s over the square root of n. So we have two different general forms for our confidence intervals for the mean. Now, which one do we use when? This one on the left we use with the z distribution if these conditions are met. First of all, sigma is known. That means I know the population standard deviation. Okay, that's our first criteria. And second, either the population is normally distributed, x is distributed normally, or my sample size is greater than 30. So if I have these two criteria met, I know I use the normal distribution, and then I can kind of follow through same as I did with my population proportion, and I use my z tables. Now the t is the one that's new here. What conditions have to be met in order for me to use the t distribution? Well, first of all, sigma is unknown. And if sigma is unknown, I use the sample standard deviation in its place. So S is known, and so that's why I have S here. S is my sample standard deviation. And then the second criteria that must be met is the underlying population is normally distributed. Okay, and then again, or my sample size is greater than 30. Now, if we have some combination of factors that do not go into either one of these categories, for instance, sigma is known but x is not distributed normal, I can't use either of these confidence intervals. I have to use other methods called bootstrapping methods or non-parametric procedures in order to figure out what's going on here. So these are the only cases that we're going to be looking at for building a confidence interval for the population mean. Now we're familiar with our z-scores already. We look at the difference between the tails. If I'm 95% confidence, I have 0.025 in each tail, and I look that up, and I have this critical value of 1.96 then. But the t distribution is what we really want to talk about here. So let's go ahead and talk about the t distribution. Now the t distribution is actually called the student's t distribution. And a long time ago, somebody was working in a brewery in Ireland, and they were talking about sampling beer and looking at consistency of the product. And they realized that they had small sample sizes, and because of the smaller sample sizes, they couldn't know what the population standard deviation was, and so they had to estimate it with the sample standard deviation, and that produced larger variability in the sample than if sigma was known. So it became a little bit more spread out than the normal distribution, but it became known as student's t distribution. So let's go ahead and look at some characteristics of the t distribution. First of all, it comes from a distribution that is not discrete but a continuous distribution, just like the normal. It's a continuous distribution. It's bell-shaped, it's symmetric, and it's centered at the mean of 0. So the mean mu is 0. It's more spread out than the normal curve usually. I can't talk about its standard deviation because there's a different standard deviation for every sample size. So the curve, the spread, is defined by the standard deviation. And that's based on our sample size. So the spread is defined by n minus 1, which are called degrees of freedom. So a lot of times these are called DF or D. So what ends up happening as my sample size increases, of course my degrees of freedom increase as well. And as my degrees of freedom increase, the t distribution approaches or gets close to the standard normal distribution. Now, if you flip your normal tables over that I handed out in class, you will see on the back your normal tables. So these are normal tables. And I'll show you how to work with the normal tables as we get a little bit further on. The one thing I want you to notice about the normal tables as we go down the side here on the left, these are my degrees of freedom. So these values over here are not n, but n minus 1. So my degrees of freedom are 2. That means that my sample size was 3. So sample size, degrees of freedom are represented down the side. Areas are at the top, and then my standard scores are in the middle. So if we get toward the bottom, as my sample size and then degrees of freedom get larger and larger, you'll notice some numbers at the bottom that probably look pretty familiar. 2.576, 1.96, and 1.645. These are similar values to what you'd find in the standard normal distribution for a 95% confidence interval. 1.645, if we come up here and have a look, area in two tails would be a 90% confidence interval. 2.576 would be for a 98% confidence interval. So these values should look pretty familiar. So these are the t-tables, and again, there's more spread in a t distribution than there is for a normal distribution. So these are just a few characteristics of the t distribution. So let's go ahead and look at a few examples of using your t-tables. So let's say that we wanted to look under our t-tables. We wanted a confidence level of 95%. And let's say we have a sample size of n equal 15. So if we're looking for that t-score, that t alpha over 2 n minus 1, what that's going to be then is t. Alpha in this case is equal to 0.05 or 5%. This means I'm 95% confident. This means I'm 5% willing to be incorrect. So this would be 0.05 over 2. And then my degrees of freedom would be 15 minus 1. Now this is a confidence interval, so I know that if this is two-sided, so I need to talk about splitting this area between the tails. So let's go ahead and draw a quick picture that will help us understand what we have going on here. So this is not the normal curve, this is the t curve with 14 degrees of freedom. It's centered at the mean, as are all t distributions. Now, I have this 95% confidence interval, so I have 95% of my areas centered above the mean, which means I have 0.025 in each tail. So the way that our t-tables read are different than the way the normal tables read, so we kind of have to get used to looking at these. With the normal distribution, that one table describes a situation where we have a standard deviation equal to 1. The t-table describes an infinite number of distributions with all sorts of different degrees of freedom. And remember, degrees of freedom define the spread of our variable. So we would pop open our t distribution. Okay, and again, we're looking for degrees of freedom of 14. Here we are, 14 degrees of freedom. So we're looking at this row right here across from 14 degrees of freedom. Now the area in two tails. The area in two tails would be a total of 5%. Okay, now notice if you want to look at this in the area of one tail, it'd be 0.025. So I have 14 degrees of freedom. The area in two tails is right up here at 0.05. So my t value would be 2.145. Remember, that's the number of standard deviations I am above and below the mean. So 2.145, negative 2.145. So my t value, or my t-score, would be plus or minus 2.145. Now, some of your calculators will have, under the distribution, the second DISTR, some of them will have an inverse t right here. If you don't have an inverse t, there's going to be directions posted on the website to see how you can program the inverse t function into your calculator so you can use this as well. So if you don't have an inverse t here, that's okay. I'll show you how to program it in so you do have it. So assuming you have the inverse t, let's go to 4 inverse t. Now this is the area to the left. Well, we would choose 0.025 here. Now degrees of freedom are 14. And then we should be able to look up the value. And I get, whoops, I get 2 of them. We'll get 3 of them. So when we look at the value, you can see it's very similar to the value that we got from the tables. So let's go ahead and paste this in. And so you can get the same values from the t distribution table that we have on the back of the normal tables, or you can use the inverse t. Inverse t is my function right here to get the same value over here. Now if I rounded this to 3 places, I would get 2.14, and the 7 would raise the 4 to a 5. So I get the same value here. Now that's not always going to be true. Now the area to the left is my first value here in the command, and the second value is my degrees of freedom, DF, degrees of freedom. Now again, if you don't have this on your calculator, I'll show you how to program it into your calculator in a separate video. So this is how I use my t-tables. So I think the best thing to do is to probably just get started working on some problems and determine, first of all, do I use the normal or the t? And then once I find the normal or the t distribution that I'm supposed to use, how to find those critical values of the z alpha over 2 or the t alpha over 2. So for this example, let's go ahead and suppose we are building a confidence interval for the population mean. And the information that I'm given is, first of all, my confidence level. Let's be 90% confident. I'm also given that my sample size is 20, and I'm given that sigma is unknown. And last but not least, my underlying distribution of x is normally distributed. So the question is, should I use the normal distribution for the distribution of the sample means? Should I use the t or neither? Okay, so A, should I use the normal? Should I be finding z alpha over 2? Or B, should I be looking at the t alpha over 2 with n minus 1 degrees of freedom? Or C, neither? Okay, so these are my options. Well, let's go ahead and look at our rundown. The level of confidence doesn't really matter in determining whether we use the normal or the t. The sample size is important, but this is really our most important piece right here, sigma unknown. So if we go back and look at our criteria, I have sigma unknown, x distributed normal, n equal 20. So sigma unknown goes over here on the right if it goes anywhere at all. My underlying distribution is normal, so I'm good to go here. Now my sample size is only 20, but remember this is an or, not an and. So I would use the t distribution here. So t distribution is what I would use. And let's go ahead and try and figure out what this will look like and find that t value. Now remember, this is t with n minus 1 degrees of freedom, so that would be 19 degrees of freedom. Distributed t with 90% of the area above the middle, centered about the middle. Now what I have here is 0.05 and 0.05 in either tail now. So there's a couple different ways I can do this. Let's first of all go ahead and look at the t-tables. Now the t-tables with 19 degrees of freedom, I can see her right here, so I'm reading through this line. Now the area on the left is 0.05. So if we want to look at this as a single tail, I'd talk about 0.05. But if I want to talk about the total area split between the tails, that would be 0.10. Okay, so as I go across here, this says area in 2 tails is 0.05. That's not right. We have the area in 2 tails to be 0.10. So as we read across here, the area in two tails is right up here at 0.10. The area in one tail was 0.05 from my picture over here, and that ends up being 1.729. So my t value is 1.729. And this is the value that I would use to build my confidence interval. So this ended up looking like t 0.10 divided by 2. And then I had 20 minus 1, or 19 degrees of freedom. So I had t 0.05, 19 degrees of freedom. And that turned out to be plus or minus 1.729. So again, degrees of freedom, just as a quick review, are equal to n minus 1. 20 minus 1 is 19. So I have to look at the criteria, and then based on the criteria, I have to choose the normal, the t, or neither. Okay, let's go ahead and look at another example where we have to choose. Oh, actually up on this other one, let's go ahead and grab our calculator. Let's use the second DISTR. We're going to do inverse t to find our t value. Now this case I have 0.05 in the left-hand area. And my degrees of freedom are going to be 20, because that's my sample size, minus 1. 20 minus 1 is 19. And it looks like my t distribution, my inverse t then, would be negative 1.729. Well, that looks pretty familiar from what I had with the tables. Again, they won't always be exact, but they should be pretty close. Remember, the area to the left is the first value, and then my degrees of freedom are the second value. Okay, for this next example, let's go ahead and suppose we are building a confidence interval for the population mean. Okay, so let's go ahead and see what we're given, and then we have to choose which distribution, if either one, I should use. So in this case, we're given a level of confidence to be 99%. Sample size is 16. Sigma is known. And the underlying distribution is very skewed. So X is not distributed normal, X is distributed very skewed. So the question here, do I do A, the normal distribution alpha over 2, B, the t distribution alpha over 2 n minus 1 degrees of freedom, or C, neither? These are my choices. Well, if we look at our criteria, sigma known has to have one of two things. It has to have X is distributed normal, or my sample size has to be greater than 30. So sigma, sigma known here. So this is my case, sigma known. X is not distributed normal, and my sample size is less than 30, so I can't use the normal distribution. I can't use the t distribution because sigma is known. This is only for sigma unknown. So in this particular case, I would use neither. Okay, because basically I have this very skewed distribution, and my standard deviation is known, and my sample size isn't large enough to overcome the skewed distribution. So that's kind of the logic that you have to go through when you're choosing which correct distribution to use. So I don't have to look up anything for this case because I'm not using either the z, the normal, or the t. Now, in actuality, there's other distributions out there to use, but we just don't know what they are yet. So for this third one, let's go ahead and suppose we are building a confidence interval for the population mean. Okay, so now we have to decide what distribution are we using given the information. Now, given that we're looking, let's say, at a 90% confidence interval, the level of confidence doesn't really matter in that choice. It will come into play if we actually have to find the scores. And then we have a sample size of, let's say, 17 here, and sigma is 19.2, so that means sigma is known. and my underlying distribution is normal. So sigma is known, my underlying distribution is normal. I've met the first criteria and the second criteria, which is either normality or n is greater than 30. Let's go ahead and look up here real quick. I'm following off of this table. X is distributed normal or n greater than 30. Looks like to me we're using the normal distribution here. So my three options are z alpha over 2, b t alpha over 2 n minus 1, or c neither. Well, after we went through our criteria, we already decided we're going to be using the z distribution. Okay, so let's go ahead and draw our quick picture here. Scoot it in over here. Our standard normal distribution. This is the z distribution. I'm looking at a 90% confidence interval, so that means I have 0.05 in either tail. And so my z-score then I can find for my normal tables. And if I'm looking at my normal tables, the easiest one to look at is on the left. And let's go ahead and look up 0.05. And we want 0.05 on the inside of the table, and it's this asterisk. It's halfway between 1.64 and 1.65, and if we read this arrow down, they're telling me plus or minus 1.645. So my z-score is plus or minus 1.645. Now remember, we can also use our calculators for this one as well. So on this one, we do second DISTR. We would do inverse normal, which is option 3 on this calculator. The area to the left is 0.05. The mean is 0, and the standard deviation is 1. And here I get that value of negative 1.645. So we can use our calculator for the inverse normal as well. Now we don't have an inverse t function on all of the calculators, but remember, I'll post video and solutions or video and directions on how to program your calculator to give you those values. So this would be my value rounded to 3 places, 1.645. Now what we do now, since we know about the normal distribution and the t distribution, is we start building confidence intervals, and then based on these confidence intervals, we start to make decisions about data. So let's go ahead and look at an example where we're actually building the entire confidence interval. Now we always have to go back to the original criteria in order to determine whether we're using the normal distribution or the t distribution. So suppose in this example we were given that we have a distribution of values based on a sample and weight lost on a diet. And from this distribution, we want to build a 99% confidence interval. And the information that we're given is our sample size is 61. Our x bar, or our sample mean, is 4.0. So this would be pounds lost on a diet, 4.0. And then our last one would be our sample standard deviation is 5.2 pounds. Okay, so what we're looking at here then is sigma is unknown. So if sigma is unknown, but my sample size is large enough, then that means I can use the t distribution. Okay, so from this information, this implies that I can have the t distribution. So sometimes it'll ask you to start by finding the margin of error first, but I'd like to just go ahead and find the confidence interval, and then we'll piece out which each point estimate and margin of error looks like. So to get started, the general form is x bar plus or minus. We already determined the t distribution is appropriate here because sigma is unknown and my sample size is more than 30. So this is t alpha over 2 n minus 1, and then this is times s over the square root of n. So let's go ahead and start plugging in values. X bar is equal to 4 plus or minus. Now we'll look at this t-score in a little bit here. S is 5.2 over the square root of 40, or sorry, square root of n, which is 61. So this is square root of 61. Now for my t value, my alpha is 0.01, So alpha over 2 would be 0.005. My degrees of freedom would be 1 less than 61 or 60. So let's go ahead and find our our t-tables and see what we can figure out for our distribution here. Okay, so down the side, 60 degrees of freedom. So here's 60 degrees of freedom. Now let's look across the top. So area in 2 tails would be 0.01. The area in 1 tail was the 0.005. So I'm in this first column, 60 degrees of freedom. So this would be 2.660. So this is going to be our plus or minus 2.660. And the plus or minus is already taken up right here. So 4 is my point estimate. And then let's go ahead and find our margin of error. And usually they ask us to round it to 1 or 2 places. So for our margin of error, we'll have 2.660 times 5.2 divided by the square root of 61. That's my sample size, is 61. Okay, so let's round this to 1.8. So this is 1.8. So this is our point estimate. And this is our margin of error. Okay, so if they ask you to find the margin of error first, go ahead and just start building your confidence interval and we'll kind of work from there. Okay, so now let's go ahead and find the confidence interval for the population mean mu. Well, the left endpoint, and remember our intervals always go small to large, would be 4 minus 1.8. My right endpoint would be 4 plus 1.8. So the confidence interval would be 4 minus 1.8. 4 minus 1 is 3. 3 minus 0.8 is 2.2. And then in my upper I'd have 4 plus 1.8 is 5.8. Remember, our confidence intervals always go small to large. So now another way we can write this is to say that the true population mean is between 2.2 and 5.8. Now remember, this is weight lost. So if we talk about this in terms of the amount of weight lost, we can say that we're 95% confident that the true value of the number of pounds lost lies between 2.2 and 5.8 pounds. Now remember, this has to do with repetitiveness. If I did this sample over and over again with size 61, that I would expect these intervals that I built, that 99% of them would capture the true mean, and then 1 would not capture the true mean, and we hope the one that we built was one of the ones that did capture the true mean. So this is an example of finding that confidence interval. Now for the next example, we'll ask to be doing a little bit of interpretation. So for this example, let's go ahead and suppose that we have a data set that includes 103 people that we took their temperature. And out of these temperatures, we have a sample mean of 98.1 degrees Fahrenheit and a standard deviation of 0.56 degrees Fahrenheit. Now, what we're asked to do in part A is to go ahead and find the point estimate. Well, the point estimate is given to us. So the point estimate is just x bar equal 98.1 degrees Fahrenheit. Okay? Now, we're also pretty familiar with our body temperature, we say, is 98.6 degrees Fahrenheit. So we did this sample of 103 people to kind of check to see if that was true or not. So for part B, let's go ahead and construct let's do a 99% confidence interval for the true mean body temperature. So if we look at what we have here, sigma is unknown. I know S, and I know my sample size is very large here. It's definitely greater than 30, so I have to use the t distribution. Okay, so that helps us determine what distribution to use. So when I construct that confidence interval, I'm going to go after x bar plus or minus t alpha over 2 n minus 1 s over the square root of n. X bar is 98.1. plus or minus, we'll fill in this t here in a bit. S is 0.56 over the square root of n, which is the square root of 103. Now, in order to find this t distribution, I'm going to come up here and let's think about this. If we have a 99% confidence interval, that means I have 0.005 in the tail. If my sample size is 103, that means my degrees of freedom are 102. Now, I'm pretty sure in our tables we don't have 102 degrees of freedom, but let's go ahead and check. So I don't have 102 degrees of freedom. Now, if you notice, as my degrees of freedom get larger, 2.6660, 654, 648, these are getting smaller, meaning they're coming in closer and closer to the standard normal distribution. So when I'm talking about which values to use here, I'm just going to choose the closest thing I can to 102, which would be 100. So I'm going to use this value 2.626 because that is where I have 1% split between two tails, or just one tail with 0.005. So again, that was 2.626, I believe, 2.626. So what we have here then is our point estimate, 98.1, plus or minus. Let's go ahead and calculate our margin of error. So for our margin of error, I will have 2.626 times 0.56 divided by the square root of, in this case, 103. So my standard error here is 0.14, or my margin of error is 0.148985, etc. So let's go ahead and throw that in. Now, usually my math lab gives you some directions about how they would like you to report your margin of error. And in this particular case, let's go ahead and round this to 3 places. So this would be 0.145. So my left endpoint would be 98.1 minus 0.145. And I'm just going to go ahead and put this in our distribution, or our notation that says I'm actually looking at a population mean. And my upper right endpoint would be 91 plus 0.145. So let's go ahead and check that left endpoint, 98.1 minus 0.145. So the left endpoint is 97.9555. And then over here, if I add these together, I'd have 98.245. So this would be my 99% confidence interval. Now, what question could we answer from here? And that would be my part C. So part C. First of all, does the confidence interval contain 98.6 degrees Fahrenheit? Because this is kind of what we typically think that the body temperature should be. And if you notice, 98.6 is slightly out of here. So this is providing evidence that my actual true mean body temperature is actually a little less than 98.6 degrees Fahrenheit. So this is a no. 98.6 is not in that interval. So let's go ahead and look at part D. So for part D, what does this suggest about the use of 98.6 degrees as the mean body temperature? It's just one of those numbers that everybody seems to know is the 98.6 degrees Fahrenheit. Well, from here, what that looks like, because 98.6 is not even in this interval suggests the true mean body temperature is lower than or less than 98.6 degrees Fahrenheit, because this entire interval is below 98.6 degrees. So those are some of the types of inferences that you can derive based on a confidence interval. The last example that we're going to look at in this lesson is using raw data, meaning I'm not given the summary statistics, but I'm given the original values and then asked to determine a confidence interval based on the values. So I'll go ahead and write it up and look at the raw data, and then we'll answer some questions from there. Okay, so to get started with this example, suppose we have measured amounts of lead in the air, and all of these are listed in micrograms per cubic meter. So this is our raw data set. And what we're asked to do is to build a confidence interval, okay, and let's go ahead and go after a 95% confidence interval in this particular case. So build a 95% confidence interval for the true mean amount of lead in the air. Okay, now we also have to be given one other piece of information here. Let's assume that my underlying distribution for the amounts of lead in the air are distributed normal. Okay? If we don't assume that, then we can't use any of our distributions. So to get started here, we don't know sigma. Our underlying distribution is normal. Okay, so that tells us I'm using the t distribution here. Okay, so building the confidence interval, I'd have x bar plus or minus t alpha over 2 n minus 1 s over the square root of n. Well, I need to find x bar and s. For sure, the only thing I know here is my sample size 1, 2, 3, 4, 5, 6 is n, and then I should be able to find my t value as well. Now we have to think back a ways. We need to find x bar and s. So that is under second list. Oh, that's not right. It's under second. I'm sorry, it's under stat, not second list, but just regular stat. Edit. And then here we have our lists. And I have something in my list, so I'm going to have to clear that out. And then I need to put in this data set. So I have 5.4, and all of mine are going in L1. 0.9. And go ahead and try this along with me, so that way when you get to this problem in your homework, you'll have tried it and you'll be able to remember how to enter your lists into your calculator to help you do these. 0.79 and 1. Okay, so x bar. So what we do then is we go to stats, calc, one variable stats, and we do to L1. Now we don't have a frequency list on this one. Okay, so this has to be clear. And here's my one variable statistics. So basically everything I need is right here on the first screen. So we don't need to go to the second screen. Okay, so this is going to be my S. This is my x bar. So x bar, let's go ahead and go with 1.56 here. Plus or minus, the t we'll look up in a moment. S, let's go with 1.8888 over the square root of, and my sample size is 6, so this would be a 6. Let's go ahead and find my t value. Now for a 95% confidence interval, that means that for my t distribution, oops, this is my normal distribution. Let's find my t distribution. For a 95% confidence interval, that means I have 5% in total in the two tails. So I'm looking down this third column to find my number of standard deviations I am above or below the mean. Now my sample size is 6 here, which means my degrees of freedom is 5. So I'd use 2.571. So 2.571. Now remember, you can also use your calculator to help you find that value. We do second DISTR inverse t, and again, if you don't have the inverse t function, we'll help you find it by programming your calculator. Those directions will be on the website. Now if I have 95% total area in the middle, that means I have 5% in either tail, or sorry, 5% total in the two tails, which would mean I have 0.025 in the left tail. My degrees of freedom are 5 because I have sample size minus 1. And let's see what that gives us here. And I get something close to what my normal tables gave me. And if you want to use this method instead of your tables, not my normal tables but my t-tables, you can. So this would give me negative 2.571 as well. So my point estimate is 1.56. And let's go ahead and calculate our margin of error. And we'll take our margin of error out to 3 places. So I have 2.571 times 1.8888 divided by square root of 6. I'm going to scoot this here. Okay, so if we round that to 3 places, that would be 1.982. 1.982. So my left endpoint would be 1.56 minus 1.982, less than mu, because I'm looking at this as a population mean, 1.56 plus 1.982. So let's go ahead and find our left endpoint. That's the 1.56 minus 1.982. So we can see that we're getting a negative value here, so I get a negative 0.422. And then for my right endpoint, I have the 1.56 plus 1.982, 3.542. So this is my confidence interval for the true average amount of lead in the air based on samples of size 6. So let's go ahead and answer a couple of questions. Question A. If the EPA, the Environmental Protection Agency, has established an air quality standard of lead to be no more than 1.5 micrograms per meter cubed, does this confidence interval show that the lead average for this area would meet EPA standards? Well, first of all, 1.5 is in this interval, but also notice the interval goes much higher than 1.5 and it goes much less than 1.5. So this is kind of a tougher question to ask. So it says no more than 1.5. So that would mean less than 1.5, so 1.5 or less. So if we look at this, we can definitely see that the values definitely go above and below. So I think this doesn't provide evidence that it's higher or lower. To me, it's just basically saying that because of this outlier, and we'll talk about the outlier in a minute here, the true average could be larger. So the question is, does this confidence interval show that the average for this area would meet the EPA standard? I would say no, because the confidence interval has values above 1.5 micrograms per meter cubed. Okay, so that's one question. Second question, B. Is there anything about this data set that suggests the confidence interval might not be very good? So is there anything about this data set that indicates the confidence interval might not be very good? Well, if we think about it, let's go ahead and scroll back up to our original data. All of these data points are fairly tightly clustered. The 0.47 is a little bit low, but they're fairly tightly clustered. But this 5.40 is an outlier. It's very extreme. So because of that outlier, we kind of have a skewed distribution here of my sample. So that kind of comes to mind that because of that skew, this confidence interval might be very reliable. So is there anything about this that says the confidence interval might not be very good? Yes. And it's the outlier. So the outlier of 5.40 to me might throw off this data because of that extreme value. Because if that 5.40 wasn't there, I don't think our confidence interval would have been over 1.5 because none of my values were. So these are the types of questions that we can answer based on confidence intervals. Now when you're working on your homework questions, if you come up with anything that you need answered, please bring your questions to class, stop by my office. You're also welcome to go to the Math Assistance Center. As usual, let us know if you have questions. We're here to help. Good luck.